This afternoon we've got Tim Adamo visiting us from London. Tim got his DPhil from Oxford, after which he held a JRF at St John's College, Cambridge, so he went to the right place. And he currently holds a JRF at Imperial. And Tim is going to tell us about...
Yeah.
Thanks, Tim.
So I'm conscious that it's kind of a heterogeneous audience here, and so there is some specific technical result, like underlying what I'm going to say, but the idea is for you to learn something, and so if we don't get to the end, some specific technical result, that's fine. The idea is to convince you that there's something interesting going on, and so interrupt me with any questions as we go along if I'm saying something that's not clear, and we kind of won't worry about how far we get. So I'm going to start and possibly fill up an entire hour, depending on how things go, with some motivation. So very broadly speaking, the subject I'd like to talk about is something called perturbative quantum field theory. Now, for the physicists in the room, of course we know that for a generic weakly coupled quantum field theory, perturbation theory is sort of the only approach that we have to computing physical observables. For the mathematicians, what this means, I have some action functional. Call it, say, S of phi. Phi could be some scalar field, it could be a gauge connection, it could be a metric, it could be anything. I have some action functional, and I'm basically looking at extracting multilinear pieces of this action function. So throughout the talk, if I'm using some terminology that doesn't make sense to use a pure mathematician, then you should just imagine that you have some action functional and you want to extract multilinear pieces of this action functional. So it's just perturbative quantum field theory in some sense is just a variational problem, a very complicated variational problem, but something that you can just understand in terms of action functionals. So the idea is that within perturbative quantum field theory, there's certain objects that it's enlightening to compute called scattering amplitudes. Okay, and so if you're a physicist, probably you know what these things are. They basically encode the probabilities for particles that we throw in from very far away to interact with each other and come out in some asymptotic state that we specified beforehand. And these are the things that define cross-sections and decay rates, so they're very useful quantities to have, but they also probe all of the nonlinear dynamical complexity of a given quantum field theory, because the evolution problem from in-state to out-state is governed by the equations of motion. So if you know the scattering amplitudes of a theory at tree level, say, then you know the full nonlinearity of that theory's classical equations of motion. So scattering amplitudes are these things that you should think of them as useful data in the sense that they're both useful experimentally. You have to compute scattering amplitudes to make theoretical predictions, which you can test against experiments at particle colliders like the LHC, for instance. But they're also useful theoretically. In the sense that you can learn about the underlying mathematical structure of a given quantum field theory by looking at its scattering amplitudes. Okay, so every theoretical physicist, at least, learns how to compute such objects at low orders in perturbation theory using a technique called Fineman diagrams, which hopefully means something to some of the audience in the room. So So this is just a, you've probably, if you watch television shows like The Big Bang Theory or something, you've probably seen, diagrams that look like this, or maybe a box diagram, things like this. These such diagrams are just useful mnemonics for translating this variational problem in the mathematical definition of a perturbative quantum field theory into some concrete expressions which you sum together and then get some number, and that number is the scattering amplitude that you're interested in. So I can give you a very brief example of this whole setup just so that we're all on the same page. So as an example, let's consider the following scalar action. So I have some d-dimensional space-time. For now, I'll be agnostic about things like signature. Of course, it matters, but we're just at tree level at the moment. So I have the usual kinetic term for my massless scalar, and then maybe I have some coupling constant. Let me call it lambda. There's some number here, and some cubic interaction term. So then the what you might call the 3-point tree level amplitude, so 3 for 3 external particles, 0 for tree level, so lowest order in perturbation theory. This is just given by evaluating the cubic part of the action, so this interaction term, on a sum of solutions to the free equations of motion, right? So in a plane wave basis, this is just given by exponential k1 plus k2 plus k3 dot x, where ki squared is 0. So these are null momenta in d dimensions. So that's, if you like, the quantum number of a massless scalar particle. And I can do this integral and get a delta function. So which conserves the momenta that I'm scattering. Okay? So this is like an extremely simple scattering amplitude for such a scalar theory, right? I just extract a cubic piece of the action and evaluate it on the multilinear combination of 3 plane waves, do the integrals, this is what I get. And the Fineman diagram you draw is just this one. Just a cubic vertex, 1, 2, 3. And that's the equivalence between the diagram and some mathematical expression. Okay, so for some people this is probably completely trivial, but I just want to get us all on the same page. So this approach has been known for well over half a century, but it has some problems. So at 3 points, there's kind of only one diagram you have to worry about, just this cubic piece. But the number of diagrams grows factorially. And that means that when you're a graduate student, you compute like 2-to-2 scattering problems and are very pleased with yourself when you're able to obtain answers. But in the real world, you need to compute amplitudes for many more external states and at much higher orders in perturbation theory. And this becomes very hard. And I don't mean hard for a person like me, but hard for a computer. So the Fineman diagram approach, although of course it makes sense and it's well defined, it becomes kind of functionally not very efficient. It also obscures hidden simplicity. Which can emerge at the end of your calculation. So in general, you have many, many diagrams that you have to sum up, and each diagram is not gauge invariant. So for instance, if we were in Puriang-Mills theory, we have some overall gauge symmetry associated with the gauge group of the theory, but each Fineman diagram is not gauge invariant on its own. Only the sum is gauge invariant. Okay? So for certain amplitudes, it's known that this enormous sum of Fineman diagrams will collapse down to an answer that you can fit on like one line. Right? So again, for the physicists in the room, this is something called a maximal helicity violating amplitude, or MHV, amps in pure Yang-Mills theory. Okay, so this, again, for if these words mean something to you, this is an amplitude, a gluon amplitude, where you have n positive helicity gluons and 2 negative helicity gluons in 4 dimensions. Tree-level computation. That entire amplitude is captured by a universal formula that fits on one line no matter how many external states you have, right? But the number of Fineman diagrams you have to sum grows factorially. So if you did the computation just for 6 points, with pen and paper using Fineman diagrams, you'd have about 300 diagrams, 300 contributions to solve. And if you cocked up one sign, or one factor of 2, you'd get an answer that would take 5 pages to write down. But if you get all the signs right, it collapses down to some simple answer that fits on one line. So in physics and mathematics and life, if you're taking a very complicated path to get somewhere very simple, it means you're taking the wrong path, right? So these Fineman diagrams apparently obstruct some nice clean or cleaner way of computing computing amplitudes. And so the idea is that over the last sort of 15 years, people have been exploring alternative approaches to the perturbative expansion in certain physically interesting quantum field theories that don't necessarily have anything to do with the traditional Fineman approach. So is everyone more or less on the same page at this point? Going once, going twice, sold? Okay. So there's one very dramatic example of this, which I'd like to sort of focus on today. So this is the case of gravity. So probably we've all heard things that, like, Einstein's theory of general relativity is not a well-defined quantum field theory. It has ultraviolet divergences, where it means that this variational problem becomes undefined at some order in the perturbative expansion. You start getting infinities. But at low orders in the perturbative expansion, so like at tree level, it's perfectly well defined for Einstein gravity. And furthermore, any crazy theory of quantum gravity that you write down, string theory, loop quantum gravity, doesn't matter. It has to reproduce those tree level answers at low energy, or else it can't be right. Okay? Because we know at low energies that Einstein gravity is a good description of the world. Okay? So even if you're someone who thinks that GR is just not a quantum field theory, you still have to care about perturbative GR at low orders, because it does a good job of describing the real world. And any great UV complete theory of quantum gravity that you write down has to reproduce those answers, or else I at least don't believe that you have a UV theory of quantum gravity. Okay. So this is described in the usual action functional formalism by the Einstein-Hilbert action. So this is a function of say a Lorentzian metric. It has some dimensionful coupling constant, which I'll call kappa, and it's given by an integral over the space-time manifold, which in d dimensions I have some diffeomorphism invariant measure. This is the absolute value of the determinant of the metric, and then I have the Ricci scalar. Okay, so you could go away and say, all right, I'm now going to start computing tree-level Fineman diagrams using this action, right? But you would very quickly decide that that was a bad idea because this action has non-polynomial dependence on G, right? In particular through this square root of the determinant here, and also from the fact that you've had to contract some indices using an inverse metric to define the Ricci scalar curvature. So in Fineman diagram language, you get just totally horrendous, horrible Fineman diagrams. You have an infinite number of vertices. Okay? So even the off-shell 3-point vertex of GR, you need like 3 lines on an A4 sheet of paper to write it down. Okay? And at 4 points, it's just a complete mess. So there's this famous anecdote in this community that Bryce DeWitt gave one of his graduate students the problem of computing the 2-to-2 graviton amplitude in pure GR. And this poor sucker, like, this is before he had computers that could help him, right? But again, you have all these terms, and the answer fits on one line when you're done. So there's somehow this moral that Fineman diagrams are bad, but you can waste an entire 5-year PhD in the States computing just a 4-point amplitude.
What is your Q2 square?
What's
What is
that?
your Q there in Q2 square?
This is kappa, because I'm very bad at writing. And this is just, we'd call this the coupling constant, so kappa is something like square root of Newton's constant. So in Newtonian gravity, if you like. So it has mass dimension -1. Okay. So you'd never want to do perturbative calculations with GR using the Fineman diagrams of the Einstein-Hilbert action. It's just a mess. But there's this beautiful, if somewhat mysterious idea that has emerged over the last maybe 7 years called double copy. And very heuristically, the idea of this is that you can compute things in GR, or indeed in generalizations of general relativity called supergravity, by first doing a computation in a much simpler quantum field theory, which is just pure Yang-Mills theory. And then, in some sense, squaring the answer that you find. Okay? So Yang-Mills theory doesn't have the problems of infinite numbers of vertices that the Einstein-Hilbert action has. So Yang-Mills theory, just so we're all on the... This is described by an action function. We saw this in, or at least we saw the abelian version of this in Tom's talk earlier, where I have some coupling constant G, have an integral d dx, and then trace over gauge group of f mu nu. For the mathematicians, you could also write this as 1 over g squared trace f wedge star f. Okay. And this is defined on a flat background, so there's no square root g here or anything. Okay. And so here you only have 3 and 4 point vertices. And actually, these 4-point vertices, you can trivially break them apart into 3-point vertices. So really, you just have 3-point vertices here. Okay. So this is already way simpler, even at just at the level of Fineman diagrams, than the Einstein-Hilbert action is. So if this mantra, which I haven't explained to you at all what it actually means yet, if this mantra of double copy is true, then the idea is that you just forget about the Einstein-Hilbert action completely. You go away, you do some calculation in Yang-Mills theory, which might be hard. Okay? If you've ever done perturbative calculations in Yang-Mills theory, once you get beyond 4 points, it sort of becomes a... Yep.
This is just a tree level?
So good, I'll elaborate, but for now let's say it's at tree level. People have pushed it beyond tree level though. So the state of the art is 5 loops, which is pretty crazy actually. If you think about doing a 5-loop calculation in this theory, I mean it's actually a supersymmetric completion. Yeah, I mean exactly, in anything, it's just sort of unthinkable. And the point is that, again, I'll just sort of repeat some of the mantras one hears in this field, is that I think even if you get to like a 4-loop diagram in this theory, you have more diagram contributions than you have cells in your brain. So like you can't even get like a computer that will store an integer that big, right? So it's like literally hopeless. You just can't do. It's just never going to work. So the fact that you can make any progress at all is kind of a miracle. And the idea is that a gauge theory calculation might be difficult for a human, but it's tractable, and certainly tractable for a computer. It's certainly tractable for the right human operating the right computer. And then if you kind of know what this squaring means, then you can obtain some answer. And you might ask how you know the answer is correct. And generally, the way people check these answers is using something called generalized unitarity. So this will be a digression for the physicists. It just means you cut propagators that you would see in your Fineman diagrams, put them on shell, and then by the optical theorem, you should recover lower loop amplitudes when you do this. And if you check all the cuts and you get lower loop amplitudes every time you do it, then you have to have the right answer. And that's basically just Cauchy's theorem. So like taking a cut is like taking a pole on the complex plane, and a function on the complex plane is uniquely defined by its poles and its residues to those poles. Okay, so that's a very sketchy overview, but now let's talk a bit more about what this actually means. Okay?
At what point will the signature become significant, if at all? You threw it away. Just
Yeah. Sort of at no point, because the way people usually do these perturbative calculations, you can actually complexify the kinematics of the particles that you're scattering. In which case, I mean, you come from the complexified world, better known as Oxford. So it's yeah. So in that sense, it doesn't matter. But if you when you get down to checking the unitarity cuts,
Right.
then you might have things like branch cuts, and then you have to worry because you need to know which branch to go on, and the signature will matter. So usually people start with some complexified kinematics, and then the people actually doing these calculations have some intuition, which I don't have for the kind of, if you like, the kind of signature that you have to impose. So it does matter, but not in I would say not in a deep way. Does that answer your question?
Mm-hmm.
Okay, so what is this double copy? So it turns out that there's several equivalent ways of understanding it, but let's try. We'll try to do both of them. Okay, so the first one, there's some intuition for this double copy that comes from string theory. Now, whether or not you like string theory doesn't matter. The point is that the low energy limit of string theory reproduces field theory. So strings, just think Riemann surfaces, and if you hear someone say an open Riemann surface, it just means like a Riemann surface that has boundaries, and if someone says a closed Riemann surface, it doesn't have boundaries, right? So open strings, closed strings. And so open string theory, the low energy limit gives gauge theory, Yang-Mills theory. Closed string theories, the low energy limit gives gravity, or GR. Of course, there's supersymmetric versions of these things, but it doesn't matter for what I'd like to say. So in string theory, your Yang-Mills, or gauge theory amplitude, is given by some correlation function. So this is, again, extracting some multilinear piece of some action functional, of some insertions of some vertex operators. So these are just some local operators in a two-dimensional quantum field theory. So they're inserted at some points, Zi, and Zi are on the disk, actually the boundary of the disk. Okay, so I have, here's my, let's call these Yang-Mills tree. These are given by some correlation function that looks like this in a low energy limit. So string theorists would call this an alpha prime goes to zero limit. It's not important to understand what that means. So I have a bunch of vertex operator insertions that I've plunked down on the boundary of my disk, n of them, say. And it's clear that I have to sum over all the different ways that I can put them down, right? So the disk, because we're on the boundary of the disk, that's just summing over cyclic orderings of n characters, right? So if I give you one ordering, say 1, 2, 3, 4 at 4 points, I have to consider that equivalent to the ordering 4, 1, 2, 3, right? Because it's just turning the disk, and that doesn't matter. But also, because this is in a CFT at on the disk, I have some Mobius invariance in play, right? There's like an SL2R isometry group that acts on the disk, okay? And that means that I can always fix 3 of the punctures to be wherever I like, just using the usual Fadeev-Popov gauge fixing procedure for that SL2R, okay? So I can always fix 3 of them, say 1, 2, and 3, to be wherever I like, and then the rest of them I have to sum over the ways of positioning the rest of them. So that actually means that this amplitude, so this A n 0, my endpoint Yang-Mills tree amplitude, can be given by a sum over permutations on n minus 3 characters. Minus 3 because we have an SL2R that we use to fix the locations of 3 of them, of some, what you would call color-ordered partial amplitudes. So these guys are just labeled by which cyclic ordering the vertex operators are in, and then you just have to sum over all the different ways of plunking down the remaining n minus 3 vertex operators. Okay? So you can understand, so you don't have to use string theory to get to this statement, but it's easier because here it's just a statement about SL2R, whereas in just field theory, you need to come up with 3 relations on color-ordered partial amplitudes, and those are the photon decoupling identity, the Kleist-Quaife relations, and something called the BCJ relations. Okay, so it's just easier to say SL2R than all these other words. Okay, so in this language, the statement of double copy is the following. I want to compute a tree-level endpoint gravity amplitude. So my notation is going to be that M is a gravity amplitude and A is a gauge theory amplitude. This is some tradition handed down to us by the ancients. I don't know why. But okay, I want to compute this endpoint tree-level gravity amplitude. I know it's going to be a nightmare, even at tree level. Using the Einstein-Hilbert action, I want to compute it in some other way. And it turns out that it's a theorem that you can compute this by taking sums over 2 of these n minus 3-fold perturbations, say alpha and beta, and then taking 2 of these color-ordered partial amplitudes and sort of tensoring them together with some n minus 3 factorial by n minus 3 factorial matrix, which I'll call S. And then the theorem is that this is the answer. Now this guy is known explicitly, this S alpha beta. This is something called the KLT kernel. So these are just the people who did this calculation to show that this was true, Kawhi, Llewellyn, and Time. And the point is that this matrix is entirely determined by the kinematic data of the scattering process. So this is just some function of the ki's. Remember, so in a massless scattering process, I have some on-shell momenta that I have to throw in. And for a Yang-Mills amplitude, I also have some polarizations. But it turns out you don't need to know the polarization information to write down this matrix. All you need to know are the ki's, or if you like, the Mandelstam invariants of the scattering problem. Okay? So again, if you're a mathematician, these words don't mean anything to you. The point is that you know this exactly. Something you can write down. If you want to know what it is, ask me afterwards and I'll tell you. Okay? So this is the statement at tree level. All I need to know are these Yang-Mills color-ordered amplitudes. Then I know what this matrix S is. I sandwich them together, and voila, I get my Einstein amplitude. Okay? And so some examples would just be, so let's just do some easy examples. The 3-point, this matrix is 1. So I just get, and there's no interesting color ordering for 3 points because I can fix it using the SL2R. So it's just the 3-point Yang-Mills guy squared. So in this sense, at 3 points, this heuristic motto over here is literally true. The 3-point gravitational amplitude is just the square of the 3-point Yang-Mills amplitude. Okay. At 4 points, it's a little more complicated. So there's only one possible permutation at 4 points. This is just a Mandelstam invariant that's basically K1 dot K2. If these formulae don't mean anything to you, don't worry. The point is just like at low points, it's relatively simple. As you crank it up, it gets more and more complicated. It looks less and less just like this mantra, because you have more and more Mandelstam crap you have to worry about, more and more terms you have to sum over. But heuristically, it's true. It's always given by some quadratic expression of the Yang-Mills guys. Now, of course, I've swept some things under the rug here, which are important. So, the important thing is that these M's and A's had better not be the whole amplitude, or else I'm getting something that's obviously crap here. Because remember, a scattering amplitude will come, for instance, with some powers of the coupling constant in front of it, and also with an overall momentum-conserving delta function, right? And that's true for the gravity amplitude as well. So I better not be squaring my momentum-conserving delta function, and I better not be squaring my coupling constant powers, because otherwise I'm going to get some big imbalance. So what these symbols actually represent is something called the stripped amplitude. You compute your scattering amplitude, strip off all the overall powers of the coupling constant and the overall momentum-conserving delta function, and then plug it into this formula, and that's what you get. So you kind of take the interesting part of the scattering amplitude.
But there must still be quite some matching going on, right? Because on the left-hand side, you've got the gravitational coupling. On the right-hand side, there's the Yang-Mills one.
Yeah, exactly. So
you've got momentum labels on the left and on the right.
So exactly. So the rule is that so every tree level endpoint amplitude comes with n minus 2 powers of the coupling constant in front of it. That's because the action goes like 1 over kappa squared or 1 over g squared, and each external state comes with 1 power of the coupling. So the idea is that on this side, you throw away an overall momentum-conserving delta function and divide by g to the n minus 2. And on this side, you put back in an overall momentum-conserving delta function and multiply by kappa to the n minus 2. And that'll take care of it. Okay? And so the way that you prove this theorem is using string theory, or the low energy limit of string theory. So this is another thing. If you walk away with nothing from today, hopefully walk away with this. Whether you like string theory as a paradigm or not, it can lead to interesting field theory statements that have nothing to do with string theory at all. Okay? So the way you prove this is by looking at monodromy relations in the two-dimensional conformal field theory of string theory, and then taking the alpha prime goes to 0 or low energy limit. Okay? So string theory is good for things other than just being a theory of quantum gravity. Okay? It can teach us things about field theories which we know are interesting.
Is it intrinsically supersymmetric?
Good. Okay, so the string theory definitely is.
Yeah.
Or if it isn't, then it has other bad problems like tachyons. But at tree level, and in the alpha prime goes to 0 limit, all of that stuff decouples as long as you only scatter ordinary gravitons or ordinary gluons. At higher loops, for sure you'll run into trouble. But what I've written here is a strictly tree level statement. So another way of saying that, maybe that's more field theoretic, is that if you just took a supergravity theory, semi-classically or at tree level, and looked at its tree amplitudes with only external gravitons, then those amplitudes are the amplitudes of general relativity at tree level. Because the graviton doesn't couple, only gravitons will flow through the tree if you only scatter gravitons. At loops, you're screwed because everything will run in the loop. But this is just a tree level statement.
Are you forced into a particular number of dimensions?
Good, again. So in some sense in string theory, the answer is yes. But at genus 0 in string theory, the thing that forces you into a particular number of dimensions in string theory is a conformal anomaly in this worldsheet CFT. Now, the short answer is that the conformal anomaly doesn't matter at genus 0. It only bites you at higher genus. And the reason for this is that if you think the conformal anomaly has to be a function of the conformally invariant coordinates on the moduli space of the theory, so at genus 0, those are just cross ratios of the vertex operator insertion locations. So the worst thing you can be out by is some conformally invariant cross ratio, which you'll be able to recognize right away in the answer and throw away. So at genus 0, it doesn't matter. At higher genus, it definitely matters, because then you can have modular functions that you have to integrate over. And if you're not in the critical dimension, you won't get an expression that's modular invariant, so your integral won't make sense. So So at tree level, again, it actually doesn't matter. These answers will be true in any number of dimensions. Even though the fully quantum mechanical string theory only makes sense, say, in 10 dimensions. Does that answer your question?
That's okay.
Can I still ask
Yeah, of course.
about the momentum labels? So on the right, I've got gluon. So the right-hand side depends explicitly on gluon momentum. doesn't it? So how are those related to the gravity?
Oh, good. Sorry. Yeah. Sorry. Let's be super specific about that. So in this correspondence, so here the gluon on-shell momenta are equal to the graviton on-shell momenta. They're both massless particles, so the idea, the mantra behind this double copy is I have some kinematic data for my graviton scattering process. The question is, how can I get that amplitude from the gluon process? And the point is that you don't have to do anything to the momenta. You just say, well, now I'm going to scatter gluons with the same momenta as these gravitons. But this is a good, you're touching on a point, which is there's a much simpler version of this double copy, which is just linear, right? So I probably should have said this first. Linear double copy. So a gluon, a mu, it carries some adjoint valued gauge index. In a flat background, we would write this as Ta epsilon mu e to the I k dot x in a plane wave basis, say. And a graviton, h mu nu, this would be epsilon mu nu e to the I k dot x. Okay? So there's no, in it, very loosely speaking, you could imagine, well, this gauge generator is getting replaced by some new Lorentz index. But the idea is that this, you should actually think of as being, if you like, the outer product of two vector-like polarizations. Now, of course, you suddenly have too many states if you do this. But the point is that such polarizations correspond to a graviton plus an anti-symmetric 2 form, which physicists would call a B field, plus a scalar. So all of these states can be written in a plane wave basis. They're linear perturbations around a trivial background, can be written in this way. And then it's obvious how to do the double copy. You just strip off this TA, put aside the e to the I k dot x, put down another copy of your transverse polarization vector so that you get here, and then just bring the same e to the I k dot x that you started with back in. And again, at tree level, in this theory, it's consistent to just scatter gravitons, and all this other stuff will
They
decouple.
behave like ghosts in a way.
Well, they don't have wrong sign kinetic term, but
In the sense that they don't contribute to your physical amplitude.
if you don't scatter them. Yeah, so you could scatter them, and then they would have well-defined non-vanishing S-matrix elements. But at tree level, you can just decouple them.
So in this, what is the gauge group precisely then in the
Oh, it doesn't matter. SUN.
that's just
Yeah. So that's another important facet of this double copy stuff is that doesn't care what the gauge group is as long as it's not abelian. Because it's very important that you have non-trivial all gluon amplitudes. If it's U1, then they're all 0, of course. Okay?
So just to summarise, on the Yang-Mills side, it's ordinary Yang-Mills, no supersymmetry.
Exactly. I mean, you can supersymmetrize it.
Let's assume we don't want
Yeah. That's
And
fine.
then on the gravity side, you've got gravity plus a few extra scalar fields and a beam.
That's right. And the point is, at tree level, you can decouple these things by just never scattering them. And then this statement is so this is like, if you like, this is the linear statement of this kind of nonlinear statement. Right? This is a statement about interactions, because there's scattering amplitudes involved, so it's nonlinear. This is just a statement about free fields.
So are you actually removing the gauge information from them?
Yeah, exactly, because
Okay.
these are color ordered amplitudes. So there's some overall trace that's been stripped off by doing this. But again, at tree level, that's not a string theory statement, that's just a fields theory statement. You can always use the fierce identity to pull out an overall color trace, which is cyclic, which is why you have these cyclic orderings labeling these partial amplitudes. You just throw it away and sum over all the different ways of doing that. Yeah, so yeah, that's another important moral of the story, is that the color stuff doesn't really matter. As long as it's there, you just end up stripping it away. Okay? And that's what you see in the linear statement, but it's also here in the nonlinear statement because you're using color ordered partial amplitudes. Okay. Now there's, yeah, we're just going to view this as an education section about the double copy and not worry about too much else. Okay, so there's another equivalent way to think about double copy at tree level. Which is in some sense like much more hands-on than this description. I mean, maybe it depends on what you think the hands-on answer is, but that's just saying that a tree-level endpoint gluon amplitude, again in pure Yang-Mills theory, can be written as a sum over cubic Fineman diagrams of some color factors associated with each diagram, some kinematic numerator factors that I'll call n, over some scalar propagators that I'll call d. Now you might ask why cubic, because there's a chordic vertex in Yang-Mills theory, but remember I made this remark earlier that actually you can kind of trivially split that chordic vertex into cubic exchange diagrams just by multiplying by s over s, t over t, or u over u in terms of Mandel's sum variables. So this isn't a deep statement. These C gammas are built from the structure constants, the F ABCs of the gauge group. So of, say, SUN. Doesn't need to be SUN, but let's just for familiarity say SUN. And these guys are functions of the KIs and the epsilons. So the polarization and momenta, they're functions on the kinematic space of the scattering. And these guys are things like, things like K1 plus K2 squared, just usual scalar propagators that might appear. Okay? So it's a straightforward statement. Any endpoint tree level Yang-Mills amplitude can be written in this way. Again, there's some overall momentum conserving delta functions, some overall powers of the coupling constant that I'm suppressing. Now, of course, these color factors are not all linearly independent. So the C gammas are not independent of each other because of the Jacobi identity. For the gauge group, the generators of the gauge group. Right? So that means that you get relations between any three, between the color factors of any three graphs. So I encourage you, if you aren't enjoying Spiegelhalter's talk later, to check this at 4 points to convince yourself that it's true. Here it really is just literally the Jacobi identity for the generators of the gauge group. Okay? Now, the idea is that there's also a similar Jacobi-like identity for these kinematic numerators. So this is actually a theorem at tree level. Now, why is this a theorem and not just a tautology? Because remember, one of the first things we said that was bad about Fineman diagrams was that they weren't gauge invariant, right? So your definition of these kinematic numerators depends on how you've split the amplitude apart into a sum over cubic graphs. So the identification of these numerators is not gauge invariant. It's gauge dependent. The theorem is that there exists a gauge for which the numerators in that gauge obey this Jacobi identity. Okay. And that is a theorem at tree level. So
Is Is this a kind of abstract existence, or do we know the gauge?
They know how to construct them.
Is it anything that we'd recognise?
Well, let me rephrase it. It's nothing I would be able to reproduce for you standing up here. But again, I invite you, if you're really not liking Spiegelhalder's talk, to check this again at 4 points.
Tom could have done this to you, you know.
He could have done. Yeah. He could have done, but he didn't. Yeah. You would all be computing super integral dynamical systems. Maybe you are. I don't know. But yeah. So at 4 points, this is a calculation that you can do on paper. At higher numbers of points, people know how to construct them explicitly. Maybe I should, I'm not one of those people, but you can, read the relevant papers and figure it out. Yep, go ahead.
Does the gauge depend on what order amplitude you're looking at?
Yeah. So for instance, at 4 points, any way that you choose to split up the sum into cubic graphs will obey this identity. It's not, you have to do a calculation to see that, but yeah. So that's why you can do this during the lecture, so to speak. If you remember your Fineman rules for Yang-Mills theory. Okay. Now the crazy thing is that this statement I can extend to loop levels, or it's at least clear how to extend it to loop levels. So here, if I do an L loop endpoint amplitude, then the only thing that changes is that I now have an integral over d dl L, and then my sum over cubic graphs. And now these kinematic numerators can also depend on the loop momenta, and these guys that depended on the ki's can also depend on the loop momenta. Okay, so that's again a theorem that you can always write in the L loop Yang-Mills amplitude in that way. And the color factors, of course, will still obey these Jacobi-like relations at any number of points, any number of loops. Now, it's not a theorem anymore. It's a conjecture that you can always find a gauge in which the kinematic numerators still obey some Jacobi-like identity. And the crazy thing, so let's get rid of all this. You definitely don't want to check this at 4 points during during the lecture. So what's crazy is that it's been shown to exist for n equal 4 and L less than or equal 5. So this is pretty crazy that people are able to get to this. So there's no theorem, there's no guarantee that they exist, or that a gauge can be found, a representation can be found.
You mean less or equal?
Yeah, I definitely mean. Yeah, that would be great, wouldn't it? Yeah, so less than or equal to 5. But very powerful people with very powerful computers have gone away and constructed them, constructed these representations that obey this Jacobi-like identity at 4 points for L less than or equal to 5. And it becomes increasingly hard, and you can tell it becomes increasingly hard because the temporal gap between their papers becomes increasingly large as you go higher and higher. Okay? But then, the next conjecture is that if you replace the color factors in this representation by another copy of the kinematic numerators that satisfy this Jacobi-like identity, you get the L loop endpoint gravity amplitude. Okay? So this is the way that people have attacked this problem of computing higher and higher loop amplitudes in supergravity theories to see whether or not they're actually UV finite or not. Okay, so I come up here, I do some hard work. The hard work is finding the representation of the L loop Yang-Mills amplitude that satisfies this color kinematics duality. So I have to work hard to try to find an expression for my L loop Yang-Mills amplitude such that it has kinematic numerators that obey these linear dependence relations. But then, once I find it, all I have to do is throw away the color factors in each term of this sum and replace them with another copy of those kinematic numerators, and I'm done. At tree level, this conjecture is also a theorem. So if you just make this replacement, it's known. And the reason it's a theorem is because it's actually equivalent to the statement. So you can again prove that using the low energy limit of string theory. And at higher numbers of points, in every instance where people have been able to do this construction, it's also true. So okay, it's not a theorem, but there's very suggestive evidence. There's no reason why it had to be true, even at n equal 4. So it's been very powerful. It's enabled people to do computations that never in your wildest dreams would you have imagined it would be possible to do. Okay, so does everyone sort of feel like they have some warm, fuzzy notion of what double copy is at this point, at least heuristically? Okay.
Can I just ask?
Yeah, of course.
On the right-hand side, we could understand why string theory was being used.
Mm-hmm.
On the left-hand side, you kind of met out. I think that it's a supersymmetric or string theory is still. Why is that playing a role here?
Good. Okay. So at tree level, this is bad. I wrote like a tree level slide and then I sort of changed it to an L. At tree level, you don't have to use string theory anywhere. It's just a field theory statement. And checking that the replacement C gamma goes to N gamma gives a gravity amplitude, you can check using unitarity methods that that's true. Now, at L loops, it also doesn't necessarily have anything to do with string theory. The question is just whether you get sensible answers after the replacement. Right? So suppose we were doing pure gravity above its critical dimension, say. So that means like at one loop, you should get infinity for these amplitudes. And you might ask, well, I know the Yang-Mills amplitudes, say, are finite at that loop order if I'm in a certain low enough dimension. How am I translating a finite answer into an infinite answer? And of course, the answer is that you're replacing something that had no loop momentum dependence by something which is generically a polynomial in the loop momentum. So the numerator here is becoming a much higher degree polynomial in the thing you're integrating over. Of course, you can generate UV divergences in this way. So yeah, so in principle, string theory doesn't have to enter on this side of it. And in fact, this is leading me on to the last point I really wanted to make here, which is that here at tree level, you have these two different approaches, and I said they're equivalent. Now, on this purely field theoretic side, no one has any idea where this stuff is coming from. Like, why should this be true? Right? If you look at the two Lagrangians, the Yang-Mills Lagrangian, the Einstein-Hilbert Lagrangian, there's no reason why there should be this relationship between them, even on shell. We already saw it. The Einstein-Hilbert Lagrangian has an infinite series of vertices, higher and higher point vertices, which the Yang-Mills action just doesn't have. Why on earth should their on-shell observables be related in this way? No one knows. At tree level, string theory gives an intuitive explanation for why that's the case, which is just that you're taking two open string amplitudes, which look like disks, and you're gluing them together into a closed string amplitude. And this gluing is accomplished by this KLT kernel. Okay? So there's an intuitive picture, at least, for why such statements might emerge at tree level. The problem is that at higher loops, there's no understanding of the right-hand side of the board in string theory. So for higher genus Riemann surfaces, the problem is that you don't get this neat chiral splitting. So somehow you should think of this as being like a holomorphic and an anti-holomorphic piece that I'm gluing together to get some complex manifold, very heuristically. And at higher genus, you can't do that because the moduli spaces just don't line up. So yeah, at higher loops, we lose completely this intuitive description that string theory gave us at genus 0, and instead we just have these like kind of godlike, miraculous calculations that people have been able to do to show that it keeps working. So I would say that like what would be really great is if someone could cook up a string theory understanding for this side, because at least then you can draw a picture and understand why it should be happening. So yeah, I should definitely emphasize this side of the board is just tree level, and actually I would say it's a problem that it doesn't extend to the other side of the board. So just in the last two or three, is that clock accurate? Probably, right?
5 minutes.
But yeah, okay, cool. So yeah, at the very end, I'll tell you the let's fit the non-trivial part of the talk into the last 5 minutes. Okay, so I just told you that there's no good understanding, field theory understanding, for why this story works. Even at tree level, we had to use string theory, right? So problems. No good field theory understanding. The string theory explanation is only at tree level.
So people have tried all sorts of weird ways of doing this.
Absolutely. They just don't work beyond some order in the number of external particles. So I guess probably the best attempt was by Byrne and Grant in the early 90s, but they only got to like 5 points. So the point is, what they do is they look at some perturbative expansion of Einstein-Hilbert, some perturbative expansion of Yang-Mills, and then they try to find some variables that basically allow them to kind of square each term. But okay, I mean, they got to some number of points, which is relatively low considering the kind of formulae that we're now able to generate at tree level. So I would say none of those attempts has been successful. There's more recent attempts by Chung and Riemann, but it's still a mess. I mean, they reduce a bit the non-polynomial complexity of the Einstein-Hilbert action, but you still have an infinite sum of terms that you have to worry about. Other people have, so some people have tried to build a dictionary for mapping classical solutions in Yang-Mills theory to classical solutions in general relativity. Now, if you could do that for any classical solution, that would be strong evidence that there is a field theory understanding lurking behind all of this. But of course, they can't do it for any classical solution. They can only do it for very special ones, which are known as algebraically special solutions. And in fact, they're so algebraically special that as nonlinear solutions to, well, they're so algebraically special that the nonlinear Einstein equations are linearized. So these are things called Kerr-Schild metrics. So in that sense, they're sort of perturbative solutions. So it's not surprising that there's a dictionary because this whole story is perturbative. So I'll put this in parentheses because you can view it as a problem or an interesting feature, but it's certainly not a satisfactory explanation for why the double copy exists. Okay, so the idea of what I would have told you about if I was better at organizing myself is that you want to test the robustness of double copy. So this double copy story that I've told you about is one chapter in a bigger research program that often goes under the umbrella of amplitudes. I don't actually think that's like a good name for the umbrella because the idea is to provide a rewriting of perturbative quantum field theory that doesn't rely on space-time actions. Okay, so like this double copy, the whole idea is that you're trying to get gravitational amplitudes without using Einstein-Hilbert action. So this is one example. But if this double copy stuff only works for this special class of perturbative observables, namely scattering amplitudes around trivial backgrounds, then it's not a statement about Yang-Mills theory and gravity as perturbative quantum field theories. It's a statement about miracles that happen on trivial scattering backgrounds. Okay? And that's good as far as it goes, but it certainly lowers the stakes quite a bit. So the idea is that you want to find some way to see how robust is double copy. If I push it a little bit, does it bend or does it break? Okay, and the idea is to test it by looking at scattering in non-trivial backgrounds. And so what we did last year was we looked at 3-point amplitudes in plane wave backgrounds. And for the laser physics, or QED and strong background fields people in the crowd, on the gauge theory side of this calculation, this is actually something that you know how to do, whether you know it or not. So at 3 points, the difference between the QED calculation and the pure Yang-Mills calculation in a plane wave background, it's just replacing some masses with some structure constants, basically. So things like Volkov solutions, if these words mean something to you, they have a natural map in terms of free field solutions around a gauge theory plane wave, a non-abelian gauge theory plane wave background. Okay, and you can do the same thing in gravity on a gravitational plane wave background. You can compute the amplitudes. It'll be messier than the 3-point calculation in a flat background, of course, because you don't have d-dimensional momentum conservation. But you get some answers. And it turns out the upshot is that double copy still holds. Okay? So you might say, well, gee, Tim, that's not such a deep statement. You just looked at 3-point tree level amplitudes. That's just looking at the cubic part of the classical action. So you don't need to use anything too terribly sophisticated, you might think. But actually, it is a deep result because gluon fluctuations and graviton fluctuations on plane wave backgrounds don't obey Huygens' principle anymore. So that means if you specify some initial data on a null slice, it will smear out from that null slice as time goes on. Another way of saying it is that if you throw a gluon into a Yang-Mills plane wave background, it interacts with the background. It doesn't just pass through. Okay? And the same is true for graviton perturbations on a gravitational plane wave background. What's crazy is that the tail structure of those perturbations doesn't line up at all. So remember earlier we had this linear double copy just in terms of plane waves? That doesn't work anymore on non-trivial background fields. The tail structure of a graviton perturbation is completely different from the tail structure of a gauge theory perturbation. So actually it's a miracle that the on-shell observables, the 3-point amplitudes, have any relation at all. So of course the double copy here is a little more complicated than it is on flat spacetime, but it's still basically just squaring the amplitude and then making some replacements. So anyway, I'll stop there. I think we've gone over time. And I'm sorry I wasn't able to do more than give you some words, but hopefully you learned something, if nothing else. Okay, thanks.
Questions? Tom?
Why does it work at all?
Yeah, I mean yeah. So
what I mean is so it is. I mean there are simpler kind of maps between different fields. If you think of basic bosonizations in 2D or so, where basically you can, and even there, these are particularly simple field theories, but even there, if I want to express a boson, or relate bosons to fermions on a microscopic level, it's a horrendously complicated map, and it never worked in higher dimensions.
Mm-hmm.
So should I think of this as telling me that there is a highly complicated non-linear map which relates gravitons and gluons on the field level of the fields?
yeah, so maybe that I've misunderstood your question, but I would say the answer is no. So I think what the statement probably is that there's a map between on-shell perturbative observables in two different field theories on two different backgrounds. So remember when we were kind of overviewing just the basic double copy on a flat background, the question that's being asked is, how do I compute an n-point graviton amplitude perturbatively around Minkowski space? And the answer is that you first compute an n-point gluon amplitude perturbatively around Minkowski space. So now the question we're asking is, how do I compute a graviton amplitude on a gravitational plane wave metric? So you imagine some gravitational wave has happened in the past, you do your scattering problem on top of it, and you see what comes out. The answer is that you do a different scattering problem of gluons on a gauge theory plane wave background, and which background you have to set up is specified for you by which gravitational background you're trying to compute the answer on. You do that calculation and then manipulate it in some completely prescribed way, which again is like basically squaring it at 3 points, and you obtain the answer to the question you started with. What you can't do is say, I have a graviton perturbation on, so a free field, a spin 2 free field on a plane wave metric. Can I build it from a gluon perturbation, spin 1 perturbation on a plane wave gauge field background? And the answer to that is basically no. Or at least, if you provide an answer, it's going to be extremely artificial. It's not algorithmic in any sense. Not just like squaring a polarization tensor. And I mean, just to put a formula to these words I'm saying. So on again, you guys will recognize this. So on a gauge theory plane wave background, a gluon perturbation looks like TA, we'll call it epsilon tilde mu, and e to the I phi tilde. This e to the I phi tilde is your Volkov solution, so phi tilde solves the Hamilton-Jacobi equation in the background. And this epsilon mu is like some epsilon tilde flat, so what you would have in the flat background limit, plus some tail. That's a function of u, the light coordinate on which the plane wave background depends. Now, the graviton perturbation on a gravitational plane wave background, this has some piece that's like epsilon nu. So that looks good. That's like what we had in flat space. But then you get some tail here that's a function of u and of what you would call x perp, I guess. And then you have, again, some solution of the Hamilton-Jacobi equations in that metric background up the back. This epsilon, again, looks like epsilon flat plus tail. That depends only on you. So what you could do is reproduce this part of the graviton perturbation from the gluon perturbation just by kind of squaring the gluon polarization and making some simple replacements, but there's no way to account for this additional tail piece. So in that sense, I think that's the sense in which I think the answer to your question is no, that there isn't a nice map between free fields. What there is a nice map between on-shell observables. It sort of makes sense. These aren't gauge invariant things. I mean, there's sort of no reason why. It's just an accident that in flat space they line up.
My question was actually about the absence of, sorry.
I think we're probably going to have to stop
Yeah.
recording it down for the next talk.
Yeah, sure.
But let's thank the speaker again.
Yeah.
I was thinking about when the simpler setting, when there is no. You have to think of like,